is Jen Gray, and I am the Process Control Systems Manager at NAND Flash for our run-to-run department. You guys will hear a little bit more about what that exactly involves. There's a couple of our team members on the run-to-run team. I'll have them introduce themselves.
Darren Anderson. I got my master's in chemical engineering from BYU in '96, and so I've been since that time pretty much with Micron and then NAND Flash, and I worked for a little while in the dry etch area. I don't know if any of the interns worked in dry etch, and now we're in PCS over dry etch in one process.
Nick Sylvester. I did my undergrad work here at BYU, and then I hate to say it, but I went to the U for my graduate work. And got a master's there in mechanical engineering, and I've been with NAND Flash for about 5 years now, almost full time since I got out of school, and I've been in the PCS group for 2.5 years, and I work in an area called CMP and also diffusion, so I'll get into those a little bit later, but it's a fun job. So
they love what they do. Okay, so I'm going to get started here. A little bit of overview. Not a lot of people know what NAND Flash is. I'll have some slides on that in a minute, but first I wanted to show you visually kind of what we're all about. Okay, this is called a silicon wafer. This is a 12-inch silicon wafer. So at NAND Flash, we manufacture NAND Flash memory on silicon wafers. So normally it starts with the bare silicon wafer, and we build layer upon layer a design that ends up being a NAND Flash chip. Okay, so each chip, sometimes we call them die, are one little square on here. So depending on the design and the size of the die, we can have anywhere between 200 to 1,200 individual die on a single wafer. Okay, and when we process wafers, we process them in lots of 25. So there's 25 wafers in what we call a FOUP. So this material runs through our enormous factory all together in a FOUP and gets processed. We have 500 plus processing steps from start to finish to get this done on the wafer form. Now when it leaves our factory, it goes to an assembly plant and they get put in package chips. You know, this is kind of what most people are used to, just small package chips, right? If you were to slice open this package chip, you find anywhere between 1 to 4 to 8 individual die stacked on top of each other in a single package. Okay, and then with NAND Flash, a lot of our NAND Flash memory is being used for solid-state hard drives. So this is a solid-state hard drive. This is it right here. And the NAND Flash chips on this are this row right here and this row right here. Okay. So what's the best part about NAND Flash memory and having it in a solid-state hard drive? Anybody? Still works. Okay? No moving parts, so I could drop it, I could throw it against the wall, I could do whatever I want with it, and it'll still work. Okay? So that's a little bit more of a visual. This is a reticle. A lot of people ask how we actually get the pattern and the design on the wafer. This is called a reticle. If you hold it up to the light, you guys can come up afterwards and look at that. You can kind of see some of the intricate designs. We have these multi-million-dollar photolithography tools basically shine light through this and shrink the image and pattern it on this wafer. And that's how we distinguish our design on the wafer, okay? So any given part type can have about 35 of these. Okay, it has to go through 35 different masking levels in order to get the product to work like it should. Okay? All right, so like Professor Hedegren said, we're NAND Flash, so we're a joint venture between Micron and Intel. We're 51% owned by Micron, 49% owned by Intel. Couldn't split it exactly down the middle, right? Someone had to own just a little bit more. But when we got started in January of 2006, you know, Micron had the technology. Intel had the money. What better way to form a company? One that has the technology, one that has the money to make it happen. And Micron already had this existing facility in Lehigh. Right here, here's a picture of what it looks like. Right up against the mountains, you know, right at the American Fort Canyon is where we're situated in Lehigh. And Micron had basically the shell of a building done with not much of anything inside. So when this joint venture was formed, they basically finished it. Finished everything on the inside, created a semiconductor fab on the inside, and put millions of dollars worth of tools on the inside to make it happen. So our building space sits on about 53 acres, so pretty large. let's see, we have 2,800 parking stalls. We have underground tunnels. We have kind of a two-tier parking lot with underground tunnels. Very handy in the winter during snowstorms. You don't have to truck across 2 layers of parking lots to get to the building. Yeah?
That's last slide. What did it mean by 300 millimeter?
12 inches. So when you hear people talk about 300 millimeter wafers, that's this size. Okay, 12-inch wafers is a 300 millimeter. Right now, 300 millimeter is kind of the latest and the greatest in the industry standard for semiconductor manufacturing. Obviously, the larger the wafer size, the more chips you can make on it, right?
And it used to be what, like 70 millimeters, or what was the old technology?
You know, it keeps changing. 2-inch wafers, 3-inch wafers, 6-inch wafers, 8-inch wafers to 12-inch wafers. There's actually companies out there looking at 15-inch wafers. So when you change, the costly part about changing wafer size is you have to change all your tools, the tooling for them, right? Because the tools are expecting a specific size of wafer to pick up and handle and, you know, sit on a chuck within a tool. So when you hear about fabs going from like an 8-inch wafer to a 12-inch wafer, they're dumping a lot of money into their tools to actually make them capable of manufacturing larger size wafers. Okay? So I know some people are really big into the numbers, so here's kind of what we're all about here. You know, our facility, like I said, it's huge. We've expanded our clean room over 40% in the past 6 years. We're going through our most recent expansion. Right now, we have called Building 40 is what we call it. So we're getting bigger. When we expand, we create more clean room space and we're buying more tools so we can manufacture more wafers. Like I said, we're on a lot of land. We do a lot of recycling of whatever we can. You know, we recycle 85% of our water. We're trying to meet almost every single environmental standard out there. We have won some awards from the state of Utah for being green and as clean as possible and not impacting the environment. Our people, we're just over 1,600 employees right now, so that's fairly large. We hire about 100 people a year. We have, because we're doing that Building 40 expansion, we have a lot of contractors on site helping finish the actual clean room work. We're world-class technical talent. You know, we try and hire the brightest individuals out there to help make this possible because it's not easy. It's definitely not easy when you can't see what you're actually manufacturing with your eye because it's so small. $100 million a year in our payroll. Our business, we make a lot of money, $2.5 billion in revenue for NAND Flash from IM Flash every year. Because we're co-owned by Intel and Micron, everything that we make goes to them. Okay, we don't ourselves sell it to anybody else. It goes to them, and then they can in turn do whatever they want with it. Let's see, 20% market share, and we'll talk about that later. And one other thing that we're really proud of is some of the semiconductor awards that we've won over the last several years, and we'll talk about that in a couple minutes. So NAND Flash, why is it so important? Why in the past 6 years has IM Flash been formed, and why are we the industry leader in it right now? A lot of it has to do with this, what end consumers are using NAND Flash for. If you look back in 2006, there's all these different applications where NAND Flash is used, computing, MP3 players, USB drives, mobile handset, kind of evenly spread. It's hard to tell on this graph right here, but in 2006, the mobile part of mobile use of NAND Flash was about 20%, meaning of all the applications using NAND Flash, 20% of it was driven by mobile applications. If you look at 2011, that jumped up to 44%. Okay, how many of you guys have bought a smartphone in the past 5 years? Almost everybody, I would hope, right? You have NAND Flash in your smartphone, okay? And that's why it's becoming a standard that everybody has an iPhone or something equivalent to it. So what do you think happens? So here's, you see the mobile's just grown tremendously here. What do you think is going to happen in the next 2 or 3 years?
Even more.
It's going to get bigger. And what do you think about computing? How many of you guys would love to take this and just put it in your computer at home? I know I would, right? I definitely want to replace my conventional hard drive with something like this. Okay. So here's applications. Obviously the one that we're most excited about is solid-state hard drives. Getting rid of conventional hard drives when you drop your laptop and all of a sudden it doesn't work, it doesn't happen anymore. Instantaneous boot up, low power consumption, so it's, yes?
How much memory is in the solid-state drive that you're showing us earlier?
This one right here, I have a little cheat sheet. Here's the actual case. This was back in 2009, January of 2009. It's our 34 nanometer product, and it was 80 gigs. It was an 80 gigabyte hard drive right there. So that was kind of industry standard for solid state hard drive back in 08, 09. Now they're, I think we've got some up in the 500 gigs for consumer laptop markets. Okay. So other applications, like I talked about, your smartphones all have flash memory, MP3 players, trying to push it more towards the computing and the laptop market, the gaming market. And how many of you know why flash is so awesome? It's on the screen, right?
Fast access.
Yeah, it's non-volatile, meaning you don't have to have power attached to it in order to have it store its memory, right? And there's no moving parts, and it's fast access and low power consumption because you don't have to have it powered on all the time. Okay, and that's why this is the latest and greatest, and this is what you're going to start seeing anything and everything going to is NAND flash memory. Okay, so keep talking about how we're the semiconductor industry technology leader. This is why. So this graph, if you look at these different colors, the blue is IM Flash. It's basically our process node size. So semiconductor companies rate themselves on how good they are by the smallest size transistor width that they're manufacturing. So in our case, we're calling it our NAND Flash cell. So smallest you can make it width-wise. So back here in kind of the 72 nanometer part of it, on the bottom axis is time, date. So back when IM Flash was formed, we were kind of the last to market in a 72 nanometer process node. So we kind of joined the industry as a company and started getting up and running. Well, then here comes 2007. We're kind of in the middle of the pack for our 50 nanometer process. And then when 2008 came around, we were actually first to market in our 34 nanometer process, where the other competitors were almost a full year behind us. So really around the late 2008, early 2009 is where we leapfrog all the other competitors manufacturing NAND Flash, became the industry leader. And you can see that ever since then, for our 34 nanometer process or 25 nanometer process and our current 20 nanometer process, we're still first to market and the first one selling it to customers. Okay? And because of this, we've won Semiconductor Inside of the Year awards for 3 years. And the one that we're most excited about right now is Semiconductor of the Year. So out of every semiconductor company manufacturing anything semiconductor, whether it's processors, memory, anything you can think of, this company awarded it to IM Flash specifically for our latest and greatest, smallest technology in NAND Flash. So we're very proud of it. I know our former interns, this award was announced while they were working with us this past summer. And I see the shirt there with the three-peat. When you talk about the three-peat, it's getting the 3 awards in a row. So we're very, very proud of it. It's something for a lot of people that a lot of people don't achieve. We've been able to achieve it, and we're looking forward to continuing achieving it. IM Flash moving forward. Yeah.
So is that scale, the 20 nanometers, is that done with the photolithography process as well?
Yep.
You're just improving it?
Photolithography doesn't get us down to the transistor width or that NAND cell width. There's additional processing manipulations that we have to do to the flow to get it that way. The smallest dimension that a photolithography scanner can pattern right now is about 40 nanometers. So there's other creative ways that we have to do to make that pitch even smaller. Yep. Okay, so market share. We started with 0 market share when we started in 2006. We're up above 20% now. So a big chunk in the last 6 years. And then, beyond the technology side of things, what sets us apart from other companies as well as the people side of things. We have 4 core values at IM Flash that we hold true to and we don't waver on. Commitment. We're all committed to doing what needs to get done in order to have our company achieve its strategic goals. Integrity. We're truthful and respectful to everybody. We trust one another. We work with one another. We know what has to get done. Teamwork. Very collaborative in the work that we do. It's not me, mine, this is what I'm doing. It's what can we do as a team to achieve and what goals can we obtain. And then execution. We're not able to be first to market on all of these transistor shrinks if we're not executing to what has to be done from a technology point of view. So that's one thing that we feel not only on the technology side, but the people side is kind of what makes Iron Flash different. Okay, I'll turn it over to Darren and Nick.
Thanks, Jen. All right, last year I had trouble with the mouse, sorry. But, so PCS group, again, we have multi responsibilities that we take care of. One is run-to-run, which we're going to talk about here. We also talk about SPC, which is Statistical Process Control. And another thing we talk about is FPC, where we try to predict behavior of the equipment so that we can keep it running as optimal as long as we can. So what we're talking about is in our PCS group is to maintain a high quality of NAND wafers in a fast-paced manufacturing environment. That's what we want to do. So again, this is what I talked about here. You can see SPC, which is Statistical Process Control. Thank you. We'll show some charts that we use for that in a minute. And FTC was similar to that, but we kind of keep track statistically of what's happening on the different signals from the equipment in our fab, and we try to make decisions based upon that. Run-to-run control is what Nick and I do, and that's taking data from a tool and making a prediction on what's going to happen in the future and making a change to the tool so that your process runs optimally. And then we have other things that Nick's going to talk about in the future that we're hopefully going to come up with. Okay, good. So right now we have, for our run-to-run overview, as you can see there, the run-to-run is the modification of process or equipment setting between machine runs to optimize output through the use of feed-forward or feedback control methods. Hopefully, if you guys have taken some, this looks sort of familiar, where we have a signal coming out the back or the front, or at the front of the process right here, where we can make a decision based upon incoming metrology. We can feed that forward to the controller and make a decision on the tool, make a time change or temperature change, whatever variable you're working with. And then you have post metrology, which you look and you see, this is what I anticipated my process to be, but this is what I actually got, which is either close to or varying from what you expected. So then you make an additional process change to improve your process. So we work in the run-run system with it's called the Manufacturing Execution System. That's a system in our fab that kind of the glue that holds everything together and runs the wafers that Jen was showing earlier in a good manner throughout the fab. We run with recipe management, automation host, data collection, and paging and email systems for notification when things don't go or do go the way we anticipate. So one thing that Jen kind of talked about is a run, which is you have either a wafer or a lot, which is the set of 25 wafers that we mentioned earlier, going into an equipment, piece of equipment, and then you based upon, well, that's what runs in the equipment. So that can either be a wafer or a larger set of wafers. You have a lot, which is the set of 25 wafers, wafer, which Jen showed you earlier, and the die, which makes up the wafer. And types of control, you may have seen, we'll call them CISO, which is a single input, single output control. Typically we use that in EWMA, or exponentially weighted moving average control that you may have seen. You guys talked about that.
We haven't talked about that.
So that'll be as you'll have a signal coming out, you have a lambda or a weighting factor. So if you're off by a certain amount on your post metrology that you didn't anticipate, you don't necessarily want to make a full adjustment based upon how far off you are. You want to say, I trust my post metrology, whatever, 30% of this entire correction I'm going to base on the current metrology that I just measured, and the rest I'm going to base on historical. So that's what EWMA kind of does. For multiple input, multiple output, or MIMO controllers, we use a different set. These a linear set of equations and we use a state space solution almost exclusively for the MIMO controller. And we'll have lot level control, so you make a decision based upon what the lot did. You'll have also wafer level control, so each wafer has its individual time or temperature or whatever. You make an adjustment on each wafer that runs in the tool. And then within wafer control, you can kind of look at the way the metrology looks across the wafer, and you can make decisions to different parts, to multiple signals based upon data. this is kind of a little bit small to look at, but as our steps to build a control, you can come and ask about these later, but I'll just go over the main headings here. So first of all, you need to control, you need to prepare what you're going to control. You need to know what you're controlling. You need to know if there's a solution, if there's a variable that you can move to make an adjustment on the tool. You need to define all that before you go in into your controller design. So then, associated with that, you need to define requirements. So my controller needs to control temperature or time or pressure or whatever. You need to know what you're controlling and what rate that will control to. And then, once we've defined all what you need to control, then we can develop the controller. What we use is a software, it's called E3, and it's a graphical-based software. I don't know if we basically, it's not necessarily coding line by line, but you'll have little blocks of code that you can link together to meet your requirements definitions. And then we'll test the controller, make sure it worked the way we want it to, and then we could deploy it to one tool and then to several tools, hopefully across the fab. And then we look to see how well we did compared to what we thought we'd do. So here's the SBC chart I kind of talked about. You'll have a center target, typically. You'll have an upper control and a lower control limit, and then you'll have an upper spec limit and a lower spec limit. These are usually defined by, I have to be within the spec window, and then your control is based upon your control limit's based upon how well you're able to meet that, and hopefully it's well within the spec limits. So you can see here, before a controller is developed, the variation that exists in the SBC chart, and then as we turn the controller on, you can see it dialing in and being a lot tighter. And so this will be the mean. You can also look at standard deviation, statistical measurements as well. So in this case, we just talked about CPK, so process capability, and we hope to improve that by significant amounts. So again, it's another look at it. You can see the variation here in the width of this bell curve, and as the controller is introduced, you see a much tighter bell curve, which then you can anticipate this product is the date I'm going to get off my tool. I'm certain within this much statistical probability that I'm going to be right when I make a decision, and that links together with all the other controllers that you have across the fab, and hopefully, well, for sure, you make a lot more quality, a higher quality product. So again, I told you before that I worked in the dry etch area. This is one of the controllers that we sort of worked on, where we have a thickness that came in pre-etch. We feed that forward to the controller, so we know, I'm off on my pre-metrology by so many angstroms, and I know my etch rate right now is another statistic, angstroms per minute, so I know how much time, or per second, I know how much time I need to adjust by how far off I am. So that the idea here is you're off in your pre-metrology. You want to bring that so that you hopefully anticipate you're right on your, so then you're kind of measuring apples to apples when you get to the post-metrology here. So then you go through a dry etch step, and sometimes we go through other processing steps, wet etch or different other processing areas, and then before you get to post-metrology, and then we, again, as I mentioned before, we make a decision based on how far off we were. Now, you guys talk about mostly continuous control, is that right? So you'll talk about milliseconds that always happens. This can be up to 12 hours by the time this measures till the time you hit here. So you have 12 hours, or it could be up to 12 hours of product that you're risking, because you don't know what's going to hit. Hopefully, statistically, we can make an educated guess, a really educated guess. So that's why we have to have such good defined control, so then we can continue to measure, to perform as the SBC chart showed earlier. Here's kind of a picture of what you'll see. So this is kind of a cross section of what the wafer looks like, because it's pre-metrology. And you measure all of these statistics here. So the dishing is called, your thickness, and your tunnel oxide between this floating gate. So this is right here. It's kind of where we store the electrons so that we can turn it on and off and measure if that cell has been programmed or not. And at the end of the etch step, this is what you're doing. We're etching all this thickness here away, and then we have some important measurements as well. This is our target of our final etch depth, and so now we want to see go from here to here, and you have all these varying controls. This dishing is not always exactly the same. The thickness varies just a little bit. You need to know all that stuff so that you can make a good recommendation for your controller. So here's the model that we derived for this one. So our edge target equals the pre-thickness minus the CMP dishing minus the target plus the tunnel oxide thickness. That's our model. So we have to hit that equation with all of our metrology to make the best recommendation as we can. So for post etch, now again we look at what our actual thickness was. So our thickness post etch minus the final etch thickness plus the tunnel oxide thickness. You have to throw all these in and make sure this is what we anticipated and this is what we got. And then we made your recommendation based upon that data. So there's some graphics on what the etch target is. This is what we're trying to. So these are all the things, the variables that have to be coordinated to for the controller to work properly. Okay, so now here's the cross section with the electron microscope that we look at. This is what we need. We need to have this thickness here, but you can see here that we've etched it too far. This has to hit perfectly, or sometimes the controller or the wafers can be scrapped. So thousands of dollars or more worth of material that you're committing to this tool, if you don't do it right, just goes in the garbage. So that's all you have to do right first time. So here's what I talked about. This is a MIMO controller. Two variables. We got etch time and gas flow that we're adjusting to hit our CGAA in the center and at the edge. So we have better uniformity across the wafer. And this is our predictive control that we're doing. So you guys talked about MPC at all a little
just
bit?
Briefly, yeah.
So again, model predictive control sounds fancy, but basically all you're doing, you're saying this is what my model is, this is what I'm predicting I'm going to hit, and then you measure and you say, well, I didn't hit exactly the way I wanted to, what I wanted to hit, and so this is what adjustment I need to make. And so again, here's you can see the high variation here, and as we introduce the controller, you see much better, tighter control. You can see that with the drop curves here off to the right as well. And now I'll turn this time to Nick to talk about a more complex problem. More fun.
That was way more complex.
I have one question for you before you sit down. How much of your size is dependent on just new photolithography, or how much do they rely on you guys to be able to reduce the variation?
I don't know if I could put a percentage-wise on it, but basically, if you look at one of those curves, and our variation is half of our process window or more, or takes up our entire process window, then we feed that forward to another step. Now it doesn't know what to expect, and so I don't know if you can put a percentage on it, but heavily involved in some areas, like the one I just showed you with the dry etch. We can't run it manually. It has to be run with the controller. Otherwise, there's so much variation coming in. Sometimes what you have coming in, you can't control that coming in. They don't have any process knobs on that step. And so, in that case, that controller is necessary, and we have to have it. If we don't have the data we need, it doesn't run, and it notifies us, so that we can go make a change or check and see what's going wrong or what data is missing, and then make adjustments.
So I would say a lot of we're controlling things in the angstrom range, right? If we're running 15 etch chambers for one process step, no two chambers of those 15 are exactly the same. So we heavily rely on feedback to keep our tools matched from a process point of view. And we rely on feed-forward to try and minimize incoming variation as possible. So what we deem critical step in our fab has to have a run-to-run control on it, because the process is capable about it. We just can't tune our chambers fast enough manually to make it manufacturable.
And also you have process movement, so one tool might move whatever 10 angstroms in a day or a week, and as that moves, we need to keep it on target. So sometimes we need to make up to like an hour recommendation. If we don't, then we're off, and our product quality went down. So.
And 5 years ago, we didn't have any control, and we were fine. Now, since we've shrunk down to 20 nanometers, there's no way we can make what we're making right now without controllers. They're pretty important. In case anybody was wondering about what Darren said a minute ago, that we have a paging system. We do. I brought a real live pager. We do have pagers. I get a lot of flack from the young men about that when I have to wear it. Sometimes they're like, what the heck is that thing? But anyway, okay, so this is another example. Darren just shared one from dry etch. This is an example from diffusion. Basically, in diffusion, we put a bunch of wafers in a big furnace, and we flow gases in the furnace, and we deposit some type of a film on the wafers. And so this over here just kind of shows what a diffusion furnace would look like. There's typically about 5 zones in there, and you can put 5 watts of wafers in there. So you can put 125 wafers in there, and it goes on what's called a boat. And the boat's made of quartz, and you just shove wafers in there, and then you shove the whole thing up in the furnace. So this presents some unique control challenges. It's definitely a MIMO problem. We've got multiple outputs, multiple inputs. And in most cases in diffusion right now, we actually stick test wafers in the boat, and then we measure the thickness of that film on those test wafers. Instead of measuring it on an actual product wafer, we do it on these test wafers. And the way that we come up with a model, this is a model right here, just a generic one where we have the top thickness, top center thickness, and then these are our process knobs right there, the temperature. So we'll adjust that top zone temperature, the top center zone temperature. Generally, we keep the center fixed, and then we'll adjust the bottom zone and the bottom temperatures. And then we also adjust the amount of time that it stays in the furnace. So that's kind of a state space linear model that we've come up with. And the way that we usually do that is just by running a DOE. We'll run a DOE and we'll change all those settings. We'll measure the outputs and we'll fit a line to it and come up with a model. So, any questions on that? Okay, so now we're going to get into the fun stuff, the math behind all this. I'm not going to get too much into it because it gets a little hairy, but so basically most of the time we use state space control. Darren mentioned that we do use some EWMA control, but most of our stuff is state space control. That is the top one is the state equation, and then you have the output equation right there, where X is your state, U is your input, W over there is what we consider our process noise, and then right here, Y is our output. That would be like your measurement, how thick of a film you deposited on the wafer. Your little f right here is any feed-forward terms that you might have. In diffusion, we usually don't have feed-forward terms. And then V is your measurement noise. So like what Darren was talking about, where you've predicted that you're going to get some output, and then you actually measure what's the difference between that the measured output and the predicted output. That's our measurement noise. So this is, we've got a state estimation horizon, or a filter horizon we call it, and we've got a prediction horizon. So with model predictive control, kind of like what Darren was talking about a minute ago, you can actually specify in how many runs you actually want to hit target. So generally, in what we do, we always want to hit it the next run because of what Darren was talking about, where sometimes we'll go 12 hours, from between running a wafer and actually getting metrology. When we make that update, we want to make an update to make it hit target the very next run. You could, in the model predictive control, say, no, I want to actually gradually get to target and hit target in 3 runs or something like that. But usually we just try and hit it on the next run. The filter horizon is what we use when we try and estimate our states. We're using historical data to estimate those states. Because you know, in the real world, we've got noise in our process, we've got noise in our measurements. If we just take a measurement and we base our decision fully on that last measurement, we might make a bad update. So we don't ever do that. We always want to consider what's happened in the past as well, so that we don't make too big of an adjustment or too small of an adjustment. So that's the filtered horizon and the prediction horizon. So this is the state estimation equation. Right there you can see that we're summing from k equals -1 to n minus 1. So that's your historical data that you have, all the last lots that you've measured. And basically, you have these two weighting matrices, Q and R. And the Q weights the process noise, the W, and the R weights the measurement noise. So generally, right now we don't have a very good way to tune these very well, because it gets pretty tricky to tune these. But basically, if you want to put less weight on the last measured lot, you'll make R smaller. So we usually keep Q at 1, just an identity matrix, and then if we want to give all the weight to the last lot measured, we make R really big, which means we fully trust our last measurement. There's hardly any measurement noise. We fully trust it. But if we want to reduce that and actually give a little bit more weight to the historical data, then we'll reduce that R value. And then we can actually add all these constraints in there as well, so that we're kind of getting an optimized solution.
Yeah, so you said this is the state space. Is there any other space that you would use for this sort of thing? Or
Not that I know. State space controls is a pretty well-known field, and they've been doing state space control since the 60s or so. So I mean, we don't use anything other than state space.
And what does that mean when you say state space?
It just means that you define states of your system, and they're either measurable or immeasurable, one of the two. But with those states, you can basically define how your system's behaving at any snapshot in time. If you know what the states are of the system, you can tell how the system's behaving.
Okay, so you can identify parameters that are like key indicators of how the state is behaving.
Yeah. And in our case, most of the states that we use as states aren't actually measurable. So, and you'll get into that kind of stuff in more state-space control, but you can use like observers and things like that to kind of estimate what that state is, since you can't, you can measure other things that then help you estimate what that state is. So, but yeah, you'll learn more about that in the state-space control class. Probably more than I know about it. Okay, so this is the prediction horizon. We call this the controller equation. So this is after you've estimated your states. You get a post-metrology and you re-estimate your states of the system, and then we want to predict what settings we should use for the next lot. So we use this equation here, and again we have these weighting matrices Q and R. And so basically, that if you had a really big Q and a small R, that basically is saying we don't care how far you move the inputs, because you as the input, we just want to hit target. So you give it a big Q and a small R. If you want it the other way around, it's basically a cost function. You know, if your inputs cost a lot, you know, if you wanted to flow more gas or something, but that costs a lot to flow more gas, then you can increase the R and make it so that it kind of balances out a little bit. And then we have all these constraints on here to help it to hopefully give us an optimized answer there.
I just had a question about that. So sometimes we're concerned about that because we don't want to wear out a valve or something like that, having to move too much. Do you ever wear out your equipment by making those adjustments, or is that not a concern?
We do, but I don't think that there's really been any analysis done on the cost of that type of stuff. Generally, we just try and hit target on the next run, because that's mostly where all of our money goes. Where it comes from is the diet. So, but yeah, we have very regularly scheduled maintenance on all the equipment and stuff, so we generally are repairing or replacing parts before they ever even fail. So, okay, I'm going to skip this slide, but basically the software we can use can handle things that get measured out of order. They'll run in one order, but they get measured out of order, and the software just kind of handles that internally. So this is the future of what we're doing. We're doing non-threaded run-to-run control, and actually that's not even the future anymore. We're doing that right now. There's another slide on that here in a minute. Performance monitoring and self-tuning. We're trying to optimize those Q and R weighting matrices to give us better, more optimized control, and then we're trying to move into the realm of virtual metrology as well. So non-threaded control, I'm just going to tell you it's awesome. We're going to skip this because we're running out of time, but basically you could have multiple tools and multiple products and all kinds of stuff kind of all feeding back into the same model, and you're just updating parts of that model based on wear fan. If you want to know more about that, you can come and see us afterwards. And then again, state estimation, optimization. Our intern actually worked on this project this summer. It was pretty cool. Basically what we want to do is have MATLAB running in the background that's constantly analyzing all of our data and updating those Q and R matrices to give us optimal control. Because we saw in the project that he did, we saw a 16% improvement by adjusting that Q and R. So hopefully we get that running in the background. So here's the demographics of our group. We're kind of spread all over the place. We've got master's degrees, we've got PhDs, we've got all different types of engineers, and so it's a great group. So where do you guys go from here? If you want to work at IMFT, you can come as an intern, apply for a job. You can talk to the people who already did an internship. It's a great experience. This is one I really wanted to hit on here. Learn your statistics really well. I know when I was here at BYU, we only had one statistics class, and I just thought, oh, this is lame. I don't care about this stuff. But in a real manufacturing environment, statistics is huge. So get into that stuff and learn it well. And then take some advanced controls classes, state space classes. Do you guys offer state space here?
We do. It's through the electrical engineering department. We offer the state space control.
All right, so we got some question and answer time. We got some questions for you guys real quick, and we got some flash drives to hand out. So,
These are what size are these, Jim?
which two companies combined to form IMFT? I think you were first there. All right, what type of memory do we produce? And it will still work. What does PCS stand for?
Process control systems.
Good. Good.
Sorry.
What feature size of current technology in mass production at IMFT?
Right here?
Yeah. What do CISO and MIMO stand for?
Single input, single output, multiple input, multiple output.
What's feedback control?
Where you're measuring the very thing that you're trying to control to spec.
Good. And you just feed it back into
Yeah,
the
you
model.
just feed it back into the process so instead of measuring the things coming into it.
What's feed forward control? It's kind of like a preemptive strike. And what's the indicator for performance analysis? Darren actually mentioned this. We didn't cover this very well.
I know Ken knows the answer. What did your intern project do?
What? Just the
What was the end result?
reduction in CPK, or improvement in CPK.
Good. CPK is your upper limit minus your lower limit. And these are control or spec limits, and divided by 6 sigma. So basically you're normalizing by the amount of noise that you have in your process. So just basically, if you had a CPK of 1, then that tells you that your limits are spaced exactly 3 sigma away from the target. Right? You're centered basically within that 3 sigma area. Bonus, name one of the core values. Who was first? Let's do that again.
Teamwork.
Teamwork. Good. All right, what questions do you guys have for us?